today it is not the regular time slot. I know it's hard for people to make it at 10 o'clock Monday morning, but our speaker, Dr. Babak Enayati, who is at the National Grid here in Waltham in Massachusetts, he has very demanding schedule. So we had to accommodate his schedule. So this is why this particular seminar is out of regular time that we have on the series. So very much look forward to, I don't think that Babak needs additional introduction. We just look forward to what he has to say. Thank you very much for making the time. Oh, just a little bit of a logistic thing. Please type in the chat as the seminar goes, just any questions that you may have. And if there are clarification questions, you can raise your hand. Otherwise, at the end, we'll go through the questions submitted in the chat and have a discussion. And Babak will leave a little time for that. Thank you very much.
Thanks, Maria. Can you hear me okay?
Yeah.
Okay, awesome. So, well, thank you for the opportunity to speak to you today. So one thing, Maria, I think we can, if you do receive a question in the chat, you can just, interrupt me and let's make this more like an interactive.
Okay, we can discussion.
Do that. Yeah, that's my preference too, because I don't want to just keep talking for like 15 minutes.
So Dan, can you manage that? Dan is my great.
Yes, sure.
Partner in this series, our postdoc at MIT. So anytime you want to bring the attention to Babak that there is a question, and then we'll address the question and keep going. Actually, that's much better. So thank you for pointing that out. Let's do it that way. Yeah.
Perfect. So today I am going to give you a high-level overview of how innovation can enable clean energy delivery. Okay, so both for transmission and distribution, when we talk about technologies that can enhance the performance of the grid, what do we mean by that? And where innovation stands in that big picture of delivering clean and affordable energy to the customers. At National Grid, we have 3 pillars to achieve our net zero goals. So starting with decarbonizing electricity, we are talking about, of course, like, making the grid ready for more like offshore wind integration, more distributed energy resources on the distribution system, like solar farms, and so on. Decarbonizing transportation. Transportation is one of the biggest contributors to greenhouse gas emission, and that needs to change rapidly. So we need more and more. I'm not just talking about residential charging stations for electric vehicles, but more like even like transmission system connected charging stations on the transmission lines, and like, on the highways where there's no close by distribution wires. So how do we connect transmission level, large fleet of charging stations to help electrify the transportation sector? And last but not least, we're also focusing on decarbonizing our heating. We still do have a good amount of customers still using oil for system decarbonization, for their home heating, and we do have in our plan to basically transform that heating sector from oil to electric, while still, again, going to the first category, making sure that we do have we do bring the electricity from clean sources. So when it comes to decarbonizing electricity, we're investing in technologies like grid enhancing technologies that enables our transmission system to deliver great amount of clean energy to our customers. This includes investing in solutions like dynamic line ratings, which I'm going to explain later, or other solutions, dynamic transformer ratings, power flow control, dynamic power flow control, and so on. The whole purpose of this is we need to still keep this clean energy delivery affordable, and we need to build new transmission lines only if it's necessary. So the first step is to utilize the maximum capacity that currently exists in our transmission system. And other solutions like energy storage, we're actively looking into that. We have installed energy storage. Energy storage is a tool in our toolbox for some of the grid issues, for various applications, of course, like peak shaving, some distribution reliability needs, resiliency, and so on. And we are considering to actually expand that, not considering, but we're currently working on expanding the solution to transmission. Transmission and distribution are a little bit different and when it comes to energy storage applications. And I'll get into that later on, but I just want to let you know that storage is being looked at, for transmission applications as well. So decarbonizing, I kind of touched on this, decarbonizing the transportation sector. As you add more and more EV charging stations to transmission lines and distribution lines, of course, the operation of those lines become challenging. Taking outages for many reasons like maintenance and so on can be challenging as well, right? If I want to take a transmission line out of service for a particular reason, like maintenance or line conductor testing, I would basically send a request to ISO. It has a process, takes some time. We make sure that contingency doesn't impact the reliability of the system by doing some studies. And then we take that line out of service. But what if that line now serves, 5 or 6 large plazas where we have electric vehicle charging? What do people do, during those when the system is gone? So it's complicating system operations. Our system operations need to evolve as these new technologies are being considered, and of course the heat that I mentioned earlier. So what do we do here at National Grid? Our biggest step towards this clean energy delivery is building an intelligent transmission network where we completely move away from scheduled-based maintenance to condition-based maintenance for our asset. We use the application of robotics in the system to basically improve the system safety, right? Avoid unexpected outages and so on. And so that's basically the definition of an intelligent transmission network, where we use all these smart real-time data or smart tools that give us real-time data to make better decisions. Okay, so once we have a good picture of the status of our asset, the health of our asset, the load flow in that asset, we can make better operational decisions. In order to get there, we are deploying many innovative solutions. Excuse me. And I'm going to just give you some examples of what we have done, and that are very innovative and really help the grid from system operations perspective. So starting with digital substations. Digital substations is a huge project here at National Grid. We are transforming our I should say, traditional substations or non-digital substations to digital for various reasons, which we're going to go to details later. This gives us a lot of opportunities for faster response to system outages, faster response to, like some challenges in terms of associated with renewable energy, integrate high penetration of renewable energy, and also lowered operational and maintenance costs. The other technology that I'm going to highlight here is called online monitoring. In order to deliver clean energy to the customers, the first and basic thing you need is the grid. So with that grid, if you can make condition-based, one of the basic things that you need to always keep in mind is, how can I save my transformer from catastrophic failure? How can I save my lines from failures, and so on? The best answer, or the only answer to that, is have some online monitoring technologies which give you real-time information on the health of the asset. Do not rely on only the scheduled maintenance that the manufacturer provides, because that scheduled maintenance is based on a particular temperature, weather conditions. If I install that transformer in Massachusetts and Texas, these two transformers are going to go through totally different type of weather conditions. So, installing these online monitoring technologies will help us identify the challenges, catch the failures before they really cause large system outages. And we have also deployed technology called dynamic line rating and dynamic transformer rating. This technology enables National Grid to better utilize the existing capacity of its transmission network. I'm going to show you some data later on, but moving from static line ratings and transformer ratings to dynamic ratings is a huge step, which requires a lot of investment, operational changes, and rethinking on how we're going to do system planning if we do have access to this type of data. So that's more like on the current intelligence of the grid, but we're also looking at like new tools. So how do we basically bring in new capabilities to the company and new tools that we can use? One of the areas that we're currently working on is called asset health technology, or artificial intelligence, machine learning, UAS, and robotics.
There's a question from Maria.
Yes.
You want to speak yourself?
Yes, Babak. We recognize that these condition-based monitoring and dynamic line rating, they are very important, and there is need right now. But if we look into, and some of us are getting old, right? 20 years ago, MIT was working, the LEES was working on condition monitoring transformers. EPRI was working, ABB had the technologies. Then I know that Nexon did the DLR big way, and they didn't succeed in the deployment. Can you just tell us how much now these new efforts to deploy when it's needed, how much do they draw on previous work, or are you guys looking at this as a new problem, or what's going on?
So are you talking about the resource allocation for these technologies?
No. I'm talking about transformer online monitoring that John Kasakian and Lee's people led with. There was, right. When I came to MIT, there was 12 companies from Northeast working on these condition-based monitoring for transformers. It was put into Entergy. So there is just one pilot experiment happens, and then it doesn't get deployed. Can you just address in that particular area where is there, because there is more need, or what's going on? Why is it not deployed when people invent it?
So, well, our solution is now adopted in our transformer health monitoring, like online monitoring program that we have. So online monitoring goes, of course, beyond just the health. So it has, like, say, harmonics aspect to it, and other aspects like, the GIC measurements. So the health online monitoring that we piloted was very successful, and it's currently adopted in our online monitoring program, which we're currently requiring for most of our transformer installations. So I don't know what happened in the past, why those solutions were not widely adopted. I mean, I know many utilities are working on this now, and this solution, the company that we worked with, we were happy with the results, and as I said, it's currently adopted in the program.
Okay, thank you.
Yeah, good question, Maria. Thank you. So back to the asset health.
I'm sorry, Babak, just so that we don't lose this, because you're throwing a lot of things, a lot of people who are doing research, so we just want to connect the dots. So what is the expectation on your side at National Grid that AI can bring something new to these solutions that were not done before?
Yeah, so yeah, just give me 1 second. Let me completely present the AI piece. So, and I'll get to your question. Currently we have drones, helicopters, robots, all being deployed to take some pictures of the asset condition, like our towers and lines. Look at basically the current physical status of the asset and find some defects. So those pictures come to the utilities. You can have tens of thousands of pictures being taken by these devices, and this is where I need machine learning and artificial intelligence to basically develop software that is fully trained to tell me which pictures show some defects. This is going to save a lot of O&M time for utilities to actually look at. Yeah, I have 1,000 pictures taken from this tower, and I've trained my software based on this machine learning algorithm, and so this machine learning or AI will look at all these pictures and tell me where I have a problem. Same with because currently some utilities are actually using human resources for that, and that can take a lot of time. So using machine learning will save time and improve efficiency in terms of finding the defects. We're also currently working with Boston Dynamics. You see the robot here. It's called the Spot robot. That we have already purchased this. The pilot was successful. I'm going to present this later on, but we're currently deploying this in one of our substations where it's an HVDC substation. The human cannot walk into the thyristor valve hall because of safety issues while the system is operational. So we can only do it during maintenance or outage, where we purposefully take the system down for maintenance reasons. So that's when human can walk into that thyristor valve hall. But this robot can do this anytime. So by utilizing this robot, we can have maintenance or access to these locations anytime we want, and robot can basically detect the challenges and issues way before we have a major outage. Excuse me. So moving on to renewable integration, and of course from this category perspective, we are also deploying technologies like energy storage, where it can help with power quality issues in the grid, resiliency, and reliability on the distribution side. On the transmission, the applications of energy storage, we're looking at how this can help with EV charging stations. However, from system reliability perspective and thermal violations, storage is going to have limited capability or limited applications compared to distribution, because on the transmission side, we always, the basic rule for planning is contingencies can happen anytime, it can last for a long time. So if you're designing energy storage to solve like an overload issue on a transmission line due to contingency, that energy storage needs to be able to continue to do that to mitigate that overload for a long time. So it may be in the charge mode or discharge mode, depending on the application, for a very long time. And that's not practical, basically. And it's not feasible to have that large scale energy storage that keeps charging to bring the load flow or the power flow down, because as I said, the contingencies can last like for days and weeks. So for that reason, energy storage is more like applications on the distribution side. However, on the transmission side, you can, if the overload is being caused by PV generation, where you only have PV generation during the daytime, storage can charge and discharge to go through full cycle in a day. And so the size is not going to be too big. So those are the applications that storage can help from the grid from reliability perspective. Power flow control is also another device that we're installing, where this device can is connected to our EMS system, and by sending a signal to this device, we can push the power away from a transmission line or pull more power through that transmission line. It injects a voltage to the line. This voltage has phase angle difference with the current on that line, so it basically induces a virtual impedance to the line. If the voltage is basically is behind the current, so we're in the leading condition, so current is leading voltage. So in that case, this device pushes the power away from transmission line. In the opposite direction, in the lagging condition, it pulls more power through the transmission line. So that way we can manage the amount of power that flows through our transmission lines and not just go with the line impedance, which is fixed. So let's take a deep dive into some of those solutions. Let me see if I can play this video for you. Well, apparently not. Hold on. So, whoops.
So Babak, there's another question from Ryan. Ryan, would you like to speak your question?
Yeah, Ryan, go ahead.
Yes, Dan, I can speak. Good morning, Babak. I just had a few questions. They kind of built on each other, but so the online monitoring solutions, are you able to consistently retrofit those to the existing infrastructure? Like, do you have to get a new transformer in order to enable them? Or
no, we had these transformers installed already for like maybe 10 years, if I'm not mistaken. And then we added these online monitoring devices to that transformer.
all right. So does a technician still have to be present to get readings or anything, or do any touch maintenance, operate a panel or anything to get the condition of the assets?
Yeah. So this vendor, let me start with how the pilot worked, and then I'll talk about how we're bringing all these information together. So our technician was given a live platform where he or she could just log in, and then this platform, it will basically click on the transformer that he wants to see, and all the health information of that transformer will be there. So he clicks on each one, see like what the status of the oil, oil health, and and other health parameters for the transformers are. That works for a few transformers, but once the data is, once you, like National Grid, now that we have adopted this for every single transformer, then, that brings up another issue of, well, you can't just rely on just one live platform now. So this needs to be a centralized database where all the information of all the transformers come to this database, and the technicians basically have access to that centralized point. Does that make sense?
Yes. If I got the mental model right, it sounds like the technicians read the data and then they upload it. So they're kind of acting like an air gap
Well,
between the systems.
They don't upload anything. The data directly goes to the cloud. So we're using Amazon Cloud for this, and this platform basically gets all the information from there. The technician just sitting behind a computer, maybe in his office, and just looking at the data and say, "Yeah, the transformer, it's got some problems. Let me go check."
All right, that makes sense, and that kind of leads into just the final question I had on this is, what additional technologies did you need to have to enable this online monitoring? So,
not necessarily technology, but more like the network. So we had to have fiber network in the substation to connect this device to our RTUs. So we can connect to EMS. So that was we did have this fiber, so we didn't have any problems. I think most of the stations do have that. Some that don't have RTU may not have that sort of network. But other than that, this is pretty adaptable with any sort of transformer.
All right, that makes sense. Thank you, Babak.
All right, you're welcome. Excellent questions. Okay, so let's move on to the next slide. Let's start with take a deep dive into our robotics, and then I have substation automation and dynamic line rating later. So we're utilizing robotics for two main reasons at this point. Okay, so this, of course, the scope is going to expand in the future for other applications as well, but currently we're doing this for asset inspection. Asset inspection, of course, like, the two most critical assets we have, lines and transformers. So if one of them fails, there's no power flow. So we deployed or demonstrated robotic applications for lines. So can you verify that you can see this video?
Yes, we can.
Okay, it's working. All right. So this is a robot that we demonstrated on one of our transmission lines that basically crawls across that transmission line and gives us the corrosion data. The traditional solution that most utilities use to measure the corrosion on the transmission line is you got to take an outage, cut a sample of that transmission line, send it out to the lab, and it can take months, right, to get the corrosion data of that particular small sample. So with this robot, we're basically, this robot is mounted on a live line, so no outage needed. And as time goes on and we continue to interconnect more and more clean energy resources, and also EV charging stations, taking outages is going to be very difficult and challenging. So this robot is mounted on that live line and moves with the speed of 30 meters per second and gives us the corrosion data of the line. We actually compare this data with what we have measured in the past through lab testing, and there's perfect match. And that really, that gave us the confidence that instead of taking outages, which has its own process, cutting the line, can just put the robot on the line and be done with the line span within like a minute or so. And the operator is standing on the ground, actually reading live data his laptop. So that's one solution that we completely we successfully completed, and now this application is adopted in our asset management practices. As I mentioned in the previous slide, we're also working with Boston Dynamics in one of our HVDC substations, and that pilot was very successful. So we purchased actually this robot that can autonomously walk around in the substation, inside the station or inside the tire still valve hall, look at some defects, take some pictures, and we're currently working with another vendor on the machine learning and AI perspective of analyzing large amount of data and pictures that we take from this robot, so that we don't have like one person sitting there and looking at tens of thousands of pictures. All that can be automated, and if the software catches some defects, that's when human can basically confirm that yes, there's a problem there. This improves a lot on our safety, staff safety as well. So a slide on substation automation. We are transitioning from the traditional way of building substations to new substations based on the IEC 61850 standards. All right. So in the past, the communication was hardwired, substantial building footprints. So the substations were larger. So I needed more land and areas that there are like some environmental issues. So like I had to deal with permitting challenges and so on. But moving to the digital substations where I have a smaller footprint, right? I will have like less problems in terms of permitting. More larger and more customized control panel on the traditional side. However, if we move to the digital substations, of course, the digital interface is going to be smaller. It is based on fiber optic network. Okay, so all the communications are based on that. And with this type of transformation, I have better visibility over the status of our asset at the substation, and I can remotely control them, monitor them, and as I said, it's more cost efficient, and of course smaller footprint, which allows basically faster construction of these types of substations. So imagine I have large amount of offshore wind ready to produce power built to the grid. If I build a digital substation to receive that power and hand it over to the grid, then basically it's going to take less time to do it. So I can interconnect those large offshore wind to the grid in a faster time frame. So basically, I think like we kind of covered most of what I have in this slide, because this is about online monitoring. So we are currently, most utilities that do not have online monitoring in their system, they go with time-based maintenance, which I explained, like schedule-based. Like the manufacturer, the transformer manufacturer, gives that to you and say, well, you got to check X, Y, and Z every 3 years, 4 years, 5, 10, whatever, under these conditions. So lack of data-driven intelligence, because you don't have any data, you can't really make any decisions on the health of that transformer. And if you do want to basically collect some samples, like oil samples and so on, you have to be at the site, okay? Because that's the only way you can collect that health data. And early equipment replacement. So sometimes, to avoid any large scale or catastrophic failures with transformers, you may want to replace it earlier because you don't know when that transformer is going to fail, and you don't want to wait until that day that it blows up. So there may be some actually additional few years of life of that transformer that you would miss if you don't have any data to actually capture that. So moving towards the future where you do have this online monitoring, you go to with condition-based maintenance. So once you have that information on the health of the line or transformer, sorry, not line, but transformer, you can make better decisions. When the transformer should be taken out of service to do some maintenance work, and that actually expands the life cycle of the transformer as well. Excuse me. And analytics is going to be advanced because you have better data. Real-time information will come from the transformer, and all that goes into this live platform. Oh, sorry, I turned off the laser. So all that goes into this live platform where our technicians can log in and click on each transformer on the platform and see the health condition. It's very interesting. Actually, this platform can be customized so that you receive warnings as well. So, you know, just because one technician didn't check the health of a transformer like for a week, and something happens to that transformer, you know, it doesn't mean that the tool won't do anything and will just show you the data when you log in. You can set some alarms and say, yes, if the oil health goes below this level, shoot me an email or send me a text. And it can also be color coded as well. So you can log in and see transformer X, Y, and Z show red in terms of health conditions. So you click on that and see why it's red. You can basically define the criteria in the tool for like red versus green based on the company practices. So it's a really user-friendly tool that can be utilized for this application. And of course, like, you know, alerts and notifications that I just mentioned, that it really gives you heads up on what's coming, even if you don't check this frequently. So the other tool that I have in this deck is called dynamic line rating. Okay, and this technology is I think most of you are already familiar with this. It gives us better visibility over the transmission line's existing capacity. All right, so I'll give you an example. We have, you know, the country is having really, you know, ambitious goals on interconnecting offshore wind generation to the grid, and if you go with the static ratings of the transmission lines only for your operations and planning, you will need to, you know, upgrade many of these transmission lines in the near future, reconductor them or build new ones, and that's really not economical. So how do we make sure that we can use existing capacity of our transmission lines by not just relying on static ratings while still keeping our system safe and reliable? So one of the solutions is called dynamic line ratings, where it looks at the temperature, where it looks at the wind speed, you know, icing, sag of that transmission line, and considers all of these, use the IEEE equation to calculate the rating of that transmission line. And if I can go with that transmission line, at least for system operations, I know planning can be challenging because you can't predict temperature, like, you know, weather forecast, not climate forecast. You can't do a weather forecast, like say 10 years out. You may not be able to accurately forecast the rating of a line, you know, for that period of time. So that's understandable. But for operations like day-ahead operations and so on, these devices can really do a good job with forecasting the reading of the transmission lines for like 24 hours, 48 hours, and so on. So we'll see some examples of that. Anyway, so we piloted this technology. The pilot was successful. Now this is being adopted in our business, this solution. This was installed on a 115 kV line. And the technology is installed on the tower, so no need for outages, and very straightforward. Like within like a maximum couple of hours, the installation is complete. So it's not really a timely or time-consuming installation. Some of the lessons that we learned, I'm gonna take a deep dive into this, the data comparison in the next few slides. But overall, we're getting a lot of additional capacity for clean power delivery if we can operate the system based on this dynamic ratings or forecast ratings. The challenges, the biggest challenge that we have faced so far is ability for ISOs to actually accept and utilize this data.
Yes.
Yeah, so
that was going to be my question, Babak. Yes.
Yes. So yeah, that's basically the biggest challenge we're facing. Is they're saying, well, this is going to require a lot of data integration tools, upgrades. It's going to be costly, and so I understand that ISOs, the way currently they operate the system, the dynamic ratings may not be applicable that much. However, day-ahead forecast, has a great potential to be utilized, and I have some data to show you that, why I'm making that statement. So, we need to work with ISOs to see how forecast data at least can be integrated into our operations.
Babak, if I may add, just sorry to interrupt, but I will send you offline the paper that was written. There was an experiment with NYPA, with New York Power Authority and Nexans, in which we actually showed it's quite complicated because you have to integrate this DLR data with PMU data, with SCADA data, cleanse them, and then an ISO needs to use them, or control center needs to use them to make decisions on scheduling. There was a proof of concept of that for NYPA several years ago, and I will follow up with you on that. So somebody needs to go back to ISOs now and say, look, this is needed and this is potential benefits. So thank you very much for pointing that out. Yeah.
Yes, thank you, Maria. Appreciate it.
So I will follow up on that. Yes.
There's another question from Babak and also from
Vladimir.
Yeah.
Okay, Babak, go ahead. Yeah, let's. We want to use a lot of time from Babak. Yeah.
Hi, I just have a question on the condition-based maintenance that you spoke about for the transformers. From what you had mentioned, it sounded primarily like it was setting flags using the existing data and measurements, but I was wondering if there was kind of modeling of transformer health being done and models being developed in a system of using that for preventative maintenance as well.
So all of this is based on, so what it's doing, it's basically measuring, the temperature of the coil and other factors, but ultimately modeling is a piece of this. So the answer is yes, modeling is included in this analysis.
Okay, and just to
yeah, go ahead. Sorry.
Yeah, I was just going to say, just to follow up, is the model also used for kind of future decisions? So if we kind of say, okay, if the transformer will operate at XYZ level, we may need to replace it within a month, and so that maintenance decision can be made. We have a window of a month before something might happen.
That's a good point. The answer is yes. It gives you, it doesn't give you at least what I've seen, it doesn't give you the the full life expectancy under all possible scenarios. That's kind of impossible because that requires a lot of data and you may not need it. But you can actually create, and say like, yep, so this is my load increase. This is my 10-year forecast. How can this transformer, is the transformer going to survive in the next 10 years? What's the life expectancy, and conditions like that? Is that what you're asking?
Yeah, thank you.
Yeah.
Thanks.
All right, that was like one more question.
There is one more question from Vladimir Terzia in Moscow. Vladimir?
Yes, well, firstly, thank you so much for such an inspiring and very practically oriented presentation. I'd like just to further encourage all participants who probably haven't been involved in practical project. Thanks to particularly move towards the concept of digital substation, but if we even forget this concept, which is offering a lot, thanks to new sensors and communication technologies, practically asset management is becoming, I would even say, low-hanging fruit, because we are not talking about any control action. We are just monitoring asset and making data acquisition, for example, using laser measurement units. An example, PMU's linear state estimator, it can be an area, it must be not the whole bulk power system, and based on the topology and the state of the system, dynamic line rating can be really undertaken, because traditionally it's line rating is based on a worst case analysis, but it is not always the case. We have some wind, we have, as mentioned, weather conditions used as input as well. They can encourage us to optimally utilize asset, in what means to go beyond limit, 25%, for example, overload, and then instead of building new assets. But I also mentioned the note that operational tripping schemes, they're important for system integrity. They can also rely on dynamic thermal line rating if the thermal limits are the limits in the network. So that was a project, Smart Humber Zone in the Britain. Respected speaker, are you aware about these activities at National Grid in Britain? For example, Smart Humber Zone project with operational tripping scheme and dynamic thermal line rating. There is also a IEEE paper on this.
Yes, I am aware of the, well, thank you, Vladimir, for your comment. Yes, I'm aware of, the application of this in National Grid in UK. There are some, UK, they have a great plan and vision for offshore wind integration, and they're looking at this DLR solution as one of the key enablers of that clean energy future. So yeah, I'm glad you kind of make this connection, with what's happening in National Grid in UK as well.
Yes. Now, of course, in Russia, these are new questions and on another dimensions, and we are keen to probably use this experience for National Grid. Maria, thanks for allowing me to give a comment.
Sure. Thank you very much, Vladimir. Okay, Babak, let's go.
All right. Thank you. So we kind of talked about the challenges. I'm not going to spend too much time on that. There are some cybersecurity challenges as well that need to be properly addressed. I'm not saying that it's like a roadblock, especially if you want to integrate this data to EMS directly. You got to be, reviewing or revising the ISO standards, and more like thorough pen testing, penetration testing for cyber work, and so on. So the requirements will be a bit stricter, but there are some solutions there. So let's move on to see some data that we have captured from the field. Excuse me. So we did the measurements. This is like real field data that I'm showing to you from March of 2020, okay, to July of this year, we did some data measurements. So the blue is my DLR. Orange is ambient adjusted rating, okay? So AAR, ambient adjusted rating, compared to DLR. AAR is more like restrictive in terms of wind speed and so on. So DLR really have better visibility over the wind speed, icing conditions, sag, and other parameters. Static rating, which is the rating that most planners use for, you know, to plan their transmission network. Look at the data. 94 to 97% of the time, DLR exceeds the static rating. So there's so if I want to compare DLR with static rating, I have 47% in line capacity that I'm missing if I only rely on line static rating for operations and planning. 47% is just like one line that we piloted was technology on, is a big number. So if I go with static rating, I have to just keep upgrading the existing transmission line that adds to the cost of the electricity delivery, whereas deploying DLR can help me with that and avoid that capital investment. And AAR, as I said, we've done some comparisons to the existing AAR that we use in the system. You know, that we have our processes for that AAR. So DLR still exceeds AAR by 31%. And of course, AAR exceeds a static with just like a lower number of 11%. But look at the difference, 47% to 11% if we go with dynamic line rating. As I said, real-time data may not be fully adopted in system operations the way operation works right now. We can have like planned operations, like day-ahead operations, and so on. So I have some additional information on the forecast. Okay, so these devices that we have installed on the lines, the DLR devices, can give us actually forecast data as well. So here, the orange line is the forecast that I'm getting. Even with that forecast, I have 26% increase in line capacity compared to static rating. Forecast has good, you know, safety margin. You know, if you're worried about your forecast for tomorrow, so we compared tomorrow's forecast, you know, with of course, when the tomorrow came, we did the real-time data and we compared to do the two, right? So imagine I'm doing the forecast now for tomorrow, and then tomorrow I do the real time and compare that real time with the forecast, see how accurate my forecast was. My forecast is still close to DLR with good margin that operators basically can rely on and say, yes, the forecast didn't violate my real-time data in the forecast. Even with that forecast, 26% increase in line capacity is a large number. So we need to keep that in mind, that this additional capacity can be used for clean energy delivery without the need to upgrade that line. I got this figure from a report that was published by NYSERDA in New York. General wind turbine, of course, there's like design specific, but in general, the cut-in speed, that's the time that, you know, or the speed that wind turbines start to function. You'll see the blades spinning until they go to their rated full power. The cut-in speed is 3.5 meter per second, and at 14 you're at the rated power. And again, these numbers can vary slightly based on the design as well. So if I want to only look at my DLR data for 3.5 meter per second and wind speed and above, this is the DLR that I'm getting. And this DLR is giving me actually 60% increase in line capacity. All right, this is like a huge number that we're missing. If I only go with the static rating and connect wind generation to this line, I have to keep curtailing that wind because it's going to just continue to exceed that static rating. But if I go with the DLR for a typical wind speed curve, right? I can accommodate additional 60% on that line without overloading that line. So the last slide I have is the power flow control. Well, let me go back here. So my recommendation to ISOs is to think seriously and thoroughly about the adoption of this forecast. To gain at least 26%, if you're not going to do real time, because the way our traditional operation works, at least go with forecast to gain that additional 26% in this particular example, but in other examples as well, that you can add to the existing system capacity without worrying about system overloads. The power flow control, dynamic power flow control is another device that we've installed on our transmission system. As I mentioned in my intro earlier, these devices are connected to our EMS. So through our energy management system, I can send a command signal to say, reduce the power flow on line X. And so the power flow goes down because probably, the loading is getting close to the static rating or the dynamic rating, whatever reason that is. I can send that signal and say, push the power away from that line, or I can say pull more power through that line. So that way I can manage the congestion on my transmission system. I can manage load flow in areas or the times of the day that there's more renewable generation in the grid, and I'm worried about overloading a particular transmission line. If there is capacity in the adjacent lines, I can push the power away from that line and let the power go through the adjacent lines so that I don't have to upgrade the line. So these are all the dynamic solutions that we have piloted and we have successfully adopted in the business. To conclude this presentation, I'll strongly recommend utilities and ISOs to take a deeper look at grid enhancing technologies. There's a lot of benefits sitting there. DLR and power flow control technologies are tools in the toolbox for some of the system operational and congestion relief issues. I'm also very interested in the future to see DLR and power flow controller merge together. So DLR gives us the rating of the line, power flow controller manages the power flow of that line so that they both work together. Cybersecurity, take that very seriously. That you may need to revise the cybersecurity requirements as a utility to of course address the new threats. And adoption with ISOs is one of the key steps. So start with forecast and see if you can adjust the real-time data later for emergency operations. And if you're living in a country where wind power integration is a big target, DLR can be one of the key solutions of that. And so that's my presentation. If you do have any questions, you can email me. You can find me on LinkedIn as well. So I think, Maria, I'll send you a PDF copy of this slide that you can share with the attendees so that they have all my contact information.
Thank you very much, Babak. This is, as Vladimir said, it's really inspiring and really down to earth, real questions. Unfortunately, it's 11 o'clock. I don't know how tight you are on the time, but there was one question about from somebody who said, if you are not comfortable with, they're not comfortable with using DLRs for planning because you cannot forecast well, but for operations is better, and wanted to know what you thought about that. And I think also Piotr Voroba is asking, what is the physical principle of the power flow controller? Is it essentially a phase shifter? So if you can address those quickly, I think we are running a little bit over time, but if people need to disconnect, that's fine. But if you can address those questions.
Yeah, I can stay on the line for another 15 minutes. So
that would be perfect. Okay.
Yeah. So with regards to the question on the
planning.
Yes, the planning for DLR. as you said, as I also indicated in my intro,
Right.
the challenge for planning is, well, you can't predict the weather, like say like 10 years out. Planners were like, well, you can't really use DLR in planning. So that's one aspect. The other aspect is, if you install this technology on a line that, say, like a couple of years of DLR data shows that the rating is always above the static rating, okay, then you may be able to raise your static rating to a level that basically, hits your minimum DLR, right? So if your minimum DLR is always 10% above static for a couple of years of measurements, that means there's a room to increase that static rating, and which is being basically used by planners. So there are some potential benefits there for planners. We're still investigating that. I don't have, in this particular line that we have installed, you do see that DLR sometimes goes under static, which is being seen for most of the installations. However, in some parts, months of the season or the year, you may be able to adjust the static, if DLR does not go below static, and of course that can be still gain some capacity for lines.
Yeah, just a food for thinking there. There is a big ARPA-E program on DOE on how do you manage uncertainties in open markets, right? So there is an uncertainty that comes with, nobody can plan for the next 20 years, but can you have incentives in the market so that DLR pitch in a little bit under with certain probability and so forth. So there is an active program on that, and MIT is part of it also with Lehigh. But the thing is that you cannot have, as you said, for the next 20 years. Anybody will not know the future. And it raises all sorts of questions about the incentives for managing some of the, for deploying these things. And my question earlier was along those lines. But when we talk to ISOs, probably we are going to have to address some of those. How does the operations and market, I wonder if you have any thoughts on that.
So markets, definitely for the forecast information can definitely be fed into our existing day-ahead market operations. So I don't see any major barriers besides, of course, the data management system and so on. But from the way market operates right now, you can still use the forecast data. However, yes, if you want to propose the energy market changes, of course, DLRs it can be integrated to it, but at least forecast is I think to me is the first feasible step that can be implemented easily.
Yeah, thank you. And the second question was for Piotr. What is the physical principles of the power flow controller? Is this the same as phase shifter? So
the way it works is so they cut the line, install a transformer. This transformer, and of course, some power electronics and capacitors. This is an example of 3 of these devices are on one phase, the other 3 on one phase, the other 3 on one phase. Excuse me. And the one in the middle is a transformer, and then the other 2 are the auxiliary devices on it. So this transformer, you cut the line, install the transformer, it injects the voltage to that line. So if the voltage is, so that voltage has a phase angle compared to the current that flows through the line. If that voltage is behind current, so the system is in the leading condition, which basically means it's pushing the power away from the line, because it's introducing a leading impedance, a virtual impedance to the line. If the voltage is ahead of the line, then your system is in the lagging condition, and it basically, they call it capacitive mode as well. So the leading, they call it inductive mode, lagging, capacitive. And the capacitive mode can pull more power through the line. And that's how you basically, this mode changes can be done via EMS as well.
So I don't know, Piotr, if you want to add more questions, but I want to actually, this question raises the issue about using these technologies for stability, not just for static management of constraints and so forth. So probably the power flow controller, if it has power electronics, can be used quite well for reducing the stability limits, which are often, some of the limiting constraints. So can you comment a little bit on stability limits and national grid and the systems that you are working on, and how do you see these technologies helping with that?
So Maria, can you elaborate more on your question?
So for example, I remember, I can even use the name Raf Maciello, when said that if you have, for example, HVDC lines in California fail, then if you have a little bit of storage that's controlled well, you can actually survive that before the DC line reconnects again. We can have these examples in everything. And so power flow control, which is very fast with power electronics, and I know what Piotr works on. So this is, I think that the question is motivated by that. The power shifters, phase angle regulators, they're called, the power shifters now, they're mechanically switched. So they cannot actually deal with a very fast time scale. Are these power flow controllers that you're implementing, are they capable of really reacting very fast? And if you have the right control, there are students working on that. That is a very difficult problem, but it buys you a lot. Can you talk on stability a little bit? Yeah.
Right. So yeah, thanks for elaborating on the question. So I fully agree with that. That the stability constraints for the grid is going to be impacted by this device, and I do see this as actually improving those conditions. So yes, we consider, imagine, God forbid, like we lose Sandy Pond. So it's 1.6 gigawatts of power is gone suddenly. So how these devices can be used to still keep the system going with live and stable, with that sort of contingencies for a few hours until the problem is fixed.
So there are people, I saw Rupamati Jadivada from MIT, she just finished PhD thesis at MIT along those lines. I know that Moscow people, Piotr and Vladimir, they're working on that. So how long is before, at least National Grid, forget about ISOs, before National Grid is beginning to think about adapting some of those? That would, if one were to do the study, you can easily show how much it buys you quickly. But if your controllers don't have the right logic, you can destabilize the system big way. So there is a research question there, right?
Yeah, so we are, so the pilot is complete. We're in the process of actually working with ISO. We have demonstrated we have basically presented some of our study results with 5% compensation, impedance compensation, which was a small number. Now we've moved up to larger scale in terms of study. So those studies with PSSC studies for both dynamic and so on, all that will be presented to ISO to demonstrate the benefits and the performance of this device, and how fast this device can go from different levels of impedance compensation, and how quickly it can go from capacitive to inductive and vice versa. So we are in the process of doing that. The results have been so promising so far, but now we're in the phase of them basically presenting our results to ISOs and adopting this as a general practice for us and ISOs, because without ISOs approval or I should say confirmation. We can't just keep adding devices like this because it impacts power flow, of course. But so far things have been really great, and our studies show that the device is functioning really well, and composition is enough to mitigate any load flow challenges.
So we have exceeded our welcome with you. It's 15 minutes almost after the hour. We can talk much more. And if people, as you said, if people have questions, please follow up. And I think this was so motivational. Thank you so much, Babak. And thank you everybody for getting up early and participating in this.